All right. Thank you so much, Alon. Hope you all have been enjoying the talk so far. As Alon mentioned, my name is Nicole Fronda, and today I will be telling you all about how we can use logic to understand cyber-physical systems and their behavior. By logic, I mean a mathematical language, and by cyber-physical systems, I mean systems that have these two components. There is the physical component, or the body of the system, and these things include sensors, motors, actuators, things that allow the system to interact and possibly move around in the real physical world. Then there's the cyber component of these systems, or the brains, the things that allow it to think. And these include things like computing, networking, data processing, algorithms, things that allow the system to actually accomplish the things that they were made to do. Some examples of these systems include the food delivery robots that we see rolling around campus, drones that are used for photography or mapping large areas, and self-driving cars, which I like to think of sometimes as the ultimate cyber-physical system because of the many high-tech sensors it has, the different algorithms that it uses to navigate really dynamic environments. And we're, of course, looking at the physical manifestations of these systems here. So what about the cyber parts, the brains? The brains of a cyber-physical system can also be referred to as a tech stack or a hierarchical organization of different technologies used to process data, make decisions, sometimes even multiple decisions milliseconds at a time. And it's actually quite cool to look at, quite an impressive feat of engineering. But sometimes even the engineers and designers of the systems will have a hard time debugging it or trying to fix it when things go wrong. Because as cool as it is to look at, a tech stack sometimes is not always made to make the right decisions. Sometimes it doesn't always do the right thing and exhibit good behavior. So how do we separate the good and bad behavior of these systems? And can we do it in a way that can be explained with a logical formula? So this is what I'm working on in my research, the process of logical inference to understand and characterize the expected good behavior of cyber-physical systems. And you can think of logical inference as kind of like reverse engineering the outputs of a black box system to get some sort of instructions of how it works. And with those instructions and an understanding of how that system works, we can then go and make it better, safer, more reliable. The logic I'm working on in my research is called signal temporal logic, or STL. And it's a mathematical language that includes simple Boolean operators and sometimes unique temporal operators. And these operators are used to describe signals over time. By signals, I mean properties of continuous variables, like a car's position over time. The STL formula shown here is essentially one that tells us that the car should always stay in its own lane. Makes sense, right? But why use logic in building these systems? Well, logic and formulas can be useful in tools such as automated model checking. This allows us to actually verify that the system will work as intended and satisfy the rules we put forth in these formulas. It will also let us know if there's ever a time it's going to violate these formulas. We can also use logic in automated runtime monitoring, essentially helping us detect if the system is about to violate the formula, so we can perhaps intervene and course correct. And we can also use it in controller synthesis, or automatically coding the formula as a constraint in the system, and therefore guaranteeing that the system will only output those behaviors that are consistent with the formula, the good behaviors that we want and expect. So let's go back to this problem of logical inference. How can we discover the implicit formula of the existing systems that we have so that we can use it to do all those things I mentioned and make a better system? For example, can we develop a logical inference method that can distinguish between good and bad cruise control behavior? In this graph, these signals are velocities of a train system that has a cruise control routine programmed into it. But the red signals show the cases where the train's brake system isn't working properly. And the green signals are the good behaviors that we want to enforce. So how do we discover a formula that describes those good behaviors? The answer in our case is an artificial neural network. For those of you who aren't familiar with a neural network, you can kind of think of it as a large supercomputer with all of these nodes acting as smaller processes within the computer to work together and output a decision. We don't use just any neural network for logical inference. We actually create our own neural network where we embed the nodes with the temporal logical operations from STL into the network. That way, when we train the network to distinguish between the good and bad signals, after the network is trained, we can extract the formula from the parameters of the neural network to produce a logical formula. And then this logical formula becomes that characterization of the good signals that we cared about in our data set. We call this new neural network a formula extractable recurrent neural network, or FERN for short. And here we've used FERN to infer that good cruise control behavior of the train. The dashed black line here shows the boundary that FERN identified between the good and bad signals, and FERN gives us this boundary as a formula that we can then use to go and improve upon that system. Using FERN, we can also take the formulas that it learns to communicate the behaviors of these complex systems to people who otherwise would have seen these systems as black boxes. And of course, as I said, we can also use the formula to improve the systems, make them safer, more robust, more reliable, more logical. And now I'll leave you with one last question, one last teaser, if you will. What if we could do this logical inference process by taking the formulas we learned from FERN and projecting them into some multidimensional space, not just 2D space or 3D space, but maybe even 10D, 100D. And then we can traverse this space and search for better, more formulas that can help us in our engineering processes. This could be a more efficient formula inference process, and it's the next step that I'm tackling in my research. Hopefully I can tell you all about it in the future, but for now, thank you so much for listening.